Good day, everyone, and thank you for being here today. I am Ellen Ligno, and together with my partner, Merijo Alfante, we are from MSU IIT and currently taking BS Ceramic Engineering. Today, we are here to present the paper by Ki Lai and et al. Entitled Ultraviolet Visible Spectroscopy of Graphene Oxide.
And the main objective of this study is to distinguish the dispersions of graphene oxide at different layers using ultraviolet visible spectroscopy.
Ultraviolet Visible Spectroscopy of Graphene Oxides. So for the content of our presentation, we have background of the study, theoretical background, materials and equipments, methodology, results and discussion, conclusion, and reference.
The study was entitled Ultraviolet Visible Spectroscopy of Graphene Oxides was conducted by Lai et al. That aims to investigate the characteristics of graphene oxides through ultraviolet visible spectroscopy. Graphene has a unique and fascinating properties that makes them one of the most promising materials for biosensors, therapeutics, and tissue engineering as well as electronics. In this study, the researchers distinguished the dispersions of graphene oxide at different layers using UV-vis spectroscopy. This method was utilized to study the surface film formation of graphene and its oxides that is relevant in many applications such as biomedical and electronics. Though some previous studies used characterization techniques such as atomic force microscopy or AFM, Raman spectroscopy, and transmission electron microscopy, this study was carried out through UV-vis method that measures the percentage of few layer sheets in graphene oxides dispersions efficiently and in an expensive way compared to the aforementioned techniques. Now let's move on to the theoretical background of this study. Several studies carried out on the dispersion of graphene oxides show that there are many ways to distinguish the few layer, which is 1 to 3 layers, multi-layer ranging from 4 to 10 layers, and thick layer that is more than 10 layers dispersions of graphene oxide, such as atomic force microscopy, Raman spectroscopy, and transmission electron microscopy. However, it is not widely used methods because of its expense. According to Wu et al., the differences of the spectra of the graphene oxide samples can be identified using AFM observations, where it determines the number of layers each sample had. These observations allow the layer number distribution of GO to be calculated easily. Moreover, from previous UV-vis spectroscopic studies, it was inferred that the optical absorption of graphene oxide is dominated by the pi by pi Plasmon peak near 230 nanometer. The pi by pi Plasmon peak depends on two kinds of conjugative effect. One is related to nanometer scale sp2 clusters, and the other arises from linking chromophore units such as carbon to carbon, carbon to oxygen bands. If all sp2 clusters are treated as a single phenyl ring, spectral changes in graphene oxide should depend only on the effect of chromophore aggregation. Now let's proceed to the materials and equipments used in this study. So the materials used in this study were 5 groups of graphene oxides dispersions with different mass ratios of KMnO4 to graphite. These mass ratios are 2N, 2.5N, 3N, 3.5N, and 4.5N, where 1N is equal to 10 grams, and the ratio of graphite is also equal to 10 grams. For the equipments used in the study, first we have the atomic force microscope from MFP 3DSA, Asylum Research USA. It is used to measure the thickness of the samples. Second, we have the UV-Vis spectroscope. It is used to detect the absorbance of the sample solutions. Third, Quantum 2000 Scanning ESCA Microprobe from Physical Electronics GmbH, Esmaning, Germany, a division of ULVAC PHI. It is used in X-ray photoelectron spectroscopy. Fourth, we have the X-ray photoelectron spectroscope with an aluminum K-alpha radiation of 1846.6 eV. It is used as an X-ray source in XPS. 5 is the Gaussian components. It is used to determine the peak deconvolution of the XPS data. Now let's proceed to the methodology of this study. First is the preparation of the raw materials, where graphene oxides were prepared through modified Hammers method with varying mass ratios of KMnO4 to graphite. Second is the preparation of the samples. The preparation process was as follows. First, natural graphite of 10 grams was placed in a 500 ml flask. Concentrated sulfuric acid of about 300 ml was added, and the resulting mixture was stirred slowly in an ice water bath for 10 minutes. KMnO4 with about 20 to 45 grams was added gradually over 1 hour, and then the mixture was stirred for 4 hours in ice water bath. H2O2, which is 5 weight percent or equivalent to 150 ml, was added to the mixture over 30 minutes. The resulting solid was filtered and then washed with water until the pH of the filtrate was 6 to 7. The solid was dried for 24 hours at 80 degrees Celsius to give graphene oxides. Graphene oxides was placed in distilled water, sonicated for 20 minutes, and then centrifuged at 4000 RPM for 20 minutes in a tabletop centrifuge to form an aqueous dispersion of graphene oxide. Third is the determination of the sample, where the thickness of the samples was measured, absorbance of sample solutions was determined, and the analysis of the XPS data. In the XPS data analysis, peak deconvolution was performed using Gaussian components after subtraction of a Shirley background.
Ultraviolet visible spectra of aqueous graphene oxide dispersion are presented in this figure. Two kinds of characteristic features were observed in this spectra to identify graphene oxide. The first is a shoulder at 310 nanometer corresponding to an plasmon peak. The shoulders observed for all the sample are similar. Another characteristic feature appears at 230 nanometers and corresponds to a plasmon peak. The intensity and position of this feature vary between samples. The samples formed using 4.5N and 3.5N KMnO4 exhibit a single intense peak at 230 nanometer, while that using 3N KMnO4 shows a weak peak as a high shoulder at 226 nanometer. The sample produced using 2.5 KMnO4 exhibits a low shoulder at 232 nanometer. When the mass ratio of KMnO4 is decreased to 2N, the peak or shoulder disappears. To identify why the spectra of the graphene oxide samples were different, AFM measurements were obtained to determine the number of layers each graphene oxide sample possessed. AFM observations have shown that the thickness of chemically derived single, double, and triple layer graphene sheets are approximately 0.57, 1.25, and 1.83 nanometer. And here, the interlayer spacing is calculated to be in the range of 0.6 to 0.7 nanometer. The distributions derived from AFM measurements show that the graphene oxide is composed of a single layer. As you can see in the figure, the double layers, figure 2, B, and 2G, and triple layers at figure 2C and 2H, which have an average thickness of about 0.8, 1.3, and 1.8 nanometer, respectively. The interlayer spacing is calculated to be 0.5 nanometer. Obviously, this value is much larger than that of graphite, which is normally 0.335 nanometer. Therefore, the interlayer spacing of that has undergone less oxidation than triple layer GO will be 0.335 to 0.5 nanometer. Considering that the radius of a carbon atom is less than 0.15 nanometer. The increase of thickness caused by the presence of epoxy and hydroxyl groups on both surfaces of the carbon atoms is approximately equal to the thickness of single-layer graphene oxide. Graphene oxide containing 10 layers has an average thickness of about 5.9 nanometer. AFM images of multi-layer and thick layer GO are shown in this figure. These results allow the layer number distribution of graphene oxide to be calculated easily as shown in this figure. The graphene oxide prepared using 4.5N KMnO4 is mainly 80% single layer. Graphene oxide produced using 3.5 KMnO4 is 45% double layer. The sample formed using 3N KMnO4 is a mixture of few layer and multi-layer graphene oxide. So, few layer graphene oxide accounts for 53% of the sample. That prepared using 2.5 and KMnO4 is mainly a mixture of multi-layer graphene oxide, with 4 to 10 layers account for 81% of the sample. Graphene oxide produced with 2N KMnO4 is mainly a mixture of multi-layer of 4 to 10 layer accounts for 41% and thick layer. This result suggests that graphene oxide dispersion containing high percentage of few layer, let's say 1 to 3 layers, graphene oxide can be distinguished from those with a high percentage of multi-layer or a thick layer by ultraviolet visible spectroscopy by examining the intense peak at 230 nanometer. Here, if all sp2 clusters are treated as a single phenyl ring, spectral changes in graphene oxide should depend only on the effect of chromosphere aggregation. When the mass ratio of KMnO4 is increased, the number of linking chromophore units such as CO and OC differs, as indicated in the XPS results presented in this figure. So the optical absorption intensity changed significantly. As shown in the previous figure, based on the above facts, it is inferred that the change of the ultraviolet visible absorption intensity observed for graphene oxide is caused by the conjugative effect of chromophore aggregation, which influence the plasmon peak. The thickness of triple layer graphene sheets was 1.8 nanometer when the CO ratio was 2 to 2.6. These results show that the thickness of graphene sheets depends on the content of oxygen-containing groups in the sample. The graphene oxide dispersion produced using 3.5 KMnO4 was diluted to concentration of 0.1, 0.08, 0.06, 0.04, and 0.02 milligram per ml. Ultraviolet visible spectra of the diluted solutions are shown in this figure. The lower the concentration of the dispersion of graphene oxide, the weaker its absorbance. This allows the concentration of dispersion of graphene oxide to be determined using ultraviolet visible spectroscopy. As for the conclusion, Dispersion containing few layer, 1 to 3 layers of graphene oxide can be distinguished from those containing multi-layer, from 4 to 10 layers, and the thick layer that less than 10 layers. Graphene oxide by the intense peak in their ultraviolet visible spectra at 230 nanometer. Few layer graphene oxide shows a single peak while multi-layer graphene oxide exhibits a shoulder. As the number of layers increases, the intensity of the shoulder of multi-layer graphene oxides tends to decrease. A peak or shoulder is not observed for thick layer graphene oxide. This observation allowed qualitative analysis of graphene oxide dispersions. XPS results reveal that the change of ultraviolet visible absorption intensity of graphene oxide is caused by a conjugative effect related of chromophore aggregation that influence the plasmon peak.
In this study, only few literatures were presented to support the experimental procedures as well as the significance of the characterization techniques used. Especially in the methodology section, there were not much related studies mentioned. Procedures were detailed, but methods were not elaborated well. For the results and discussion, previous studies supplemented the obtained results that make it significantly useful for further studies. However, some of the results need more clarifications and detailed explanations as it seems to be unclear, specifically for student readers who are new to this kind of study. Some of the assumptions made were on optical absorption of graphene oxides, but researchers infer that the optical absorption is dominated by the pi by pi plasmon peak near 230 nanometer. It was stated from UV spectroscopic studies that the pi by pi plasmon peak depends on two kinds of conjugative effect. One is related to nanometer scale sp2 clusters, and the other one arises from linking chromophore units such as carbon to carbon or carbon to oxygen bands. Though this study cited only a few related literatures, there were still no ludicrousness and absurdity mentioned in the paper. I recommend for future researchers to provide illustrations of the equipments used, include schematic diagram on the methods and experimental procedures, and expand the scope of the study. Future researchers may also consider providing related literatures that would support the results and discussion for future purposes, that would give clarifications to some terms, results, and theories highlighted in the study. Although they were able to present the results and discussion in a well-organized manner, where figures are presented clearly to understand their notions, nevertheless they had lacked the use of several relevant literatures that would support the results and claims that make it reliable and well-founded. Generally, this study is significant for future researches, and the literatures mentioned here were cited properly.
And here is our reference. That would be all. Thank you. Graphene